So here today we are looking at the new topic, which is design of experiment. When I was looking at this textbook, they had a very short content for this topic, design of experiment. The design of experiment. I had one course dedicated for DOE, in graduate level. So, but here we are going to just review the couple methods, and one factorial design. We're going to spend 2 or 3 sessions for this design of experiment. So it is chapter 21 on the textbook. Okay. Design of experiment or experimental design, they can be used interchangeably. It's a tool for Six Sigma, right? It's another tool that we use in Six Sigma, and it's a design, several tests or series of tests, and the idea is we want to change some variable, some factor, and then see how those factor are going to change the output. Let's see, this is a process. We have one process. There are several factors that can be manipulate. Those factors that you can change purposely, we call it controllable factors. There are some factors you cannot change. We call them uncontrollable, or sometimes we call it noise. The room temperature, outside temperature. Sometimes it might be 70 degrees Celsius, sometimes 80 degrees Celsius. These are not controllable. Some for some processes, but for some processes you have to control even their temperature. It depends on the different processes. Those factors that you cannot control, it's called noises, and noises also have effect on the output. But we are focusing on those factors that we can change. Okay. Let's say heat treatment process. Are you familiar with the heat treatment? So in heat treatment, you put your sample, steel sample, right in the furnace. So you have to keep it there for some period of time, maybe 1 hour, 2 hours. So this timing is controllable. Or you can change the temperature. You can raise it to 1,000 degrees Celsius, or 800 degrees Celsius. But this temperature also controllable, and we call it factor. So design of experiment, DOE, is a method for experimenting with a complex processes. It systematically changes variable to see that impact on the outcome. Outcome can be different from, for example, for that heat treatment outcome. What was the outcome? You tested. What was the course you took? That heat treatment. You remember? Was the ET 420? 141. Okay, so you change heat treatment process, and what was it? You were looking. Was it the hardness or strength? Hardness is one of the parameter, one of the response to those variables. So design of experiment is going to look at determine which variable affect the system. Sometimes you change timing, it's not going to affect anything. So then it's not a variable. So the idea is to find which variable has important effect, and then how determine how the magnitude of the variable affect the system, and how can we find the optimal, level. So this approach is not numerical modeling. It's not finite element modeling. This is empirical. It means you use experimental data, right? You design the experiment, and then you test it. You use the you collect the data, and then do the analyze and find what is the optimal variable. So it's based on the data that you gather. And it can be used for different industries, healthcare, manufacturing. And this DOE has several methods, trial and error. The first method, single factor experiment, that you look at one factor, one parameter. And then we have fractional factorial experiment, full factorial experiment. We have other method, Taguchi box method. But in this course, we're gonna focus on the single factor, full factorial experiment. As you know, many of the manufacturing, many of the processes, they have several variables. It's not one variable, right? And then in that situation, we have to use factorial. Factorial means you look at several factors, and then design your experiment and see how those factors affected your process, right? And then find optimal place. And it is used for Six Sigma for DMAC process. And this process, DOE is different from those processes that we use, statistical process control, right? We use process control. We were looking at the process, how the process was performing, right? So that monitoring, that analyze, is called passive. So you are not changing the process. You look at the process, you collect the information, and you want to see whether your process is in control or out of control. Okay? So you're not purposely changing any factor, any parameters. So you're just looking at that information, data, and then analyze it. Okay? So this is a statistical process control. Let's say you have a car paint shop with a robot arm, and then that is the robot that is going to apply paint. Then we use this SPC to monitor the system, whether the robot performance is correct or not, right? Then we use those X bar chart, R chart, S chart, to analyze whether the performance is in control or out of control. Okay? So SPC does not manipulate the process. Okay? It will give you alert. So this is passive. But DOE is active. So you're producing some parts, and you see the part should be better. So how can we make it better? So in that process, we are gonna improve by manipulating the factors, right? So we want to change the factors in a way that we get optimal data. So you see your process is in control, but you want to, so when you are at this level, your process is in control. There is no question about the process itself, but we want to make it better, right? And then we have a team of engineers. They will work on on the process. They see if we want to make that coating thinner, so to save some more material, what should we do? Should we reduce viscosity of the paint, or we should paint it with faster rate? So they have, these are the factors, right? So then they design the experiment, and then they see what was the outcome, right? The thickness of the paint, and then they see if they go faster rate, the robot goes faster speed, it's gonna be this much thickness. But if you use this viscosity, it's gonna make this much thickness. And then see which one is gonna have larger effect on the thickness of the paint. Okay. So they hypothesis a specific factor, and then based on that hypothesis, they design, and then they see what's the outcome of that experiment. So the difference is SPC is a passive observer, but DOE is an active engineer manipulating factors. So this one is one step ahead of SPC, right? It tries, this one tries to make the process better, improve the process. It's not going to keep the process in the current condition. Any question? So difference, we know it, right? Between these two processes, SPC and DOE. Okay. So every manufacturing processes have a lot of parameters. One of the modern manufacturing process is SLM, selective laser melting. We have one of these machines in Makerspace, probably you have seen it. It is a EOS 290, right? 290. So what is that process? It has a powder of the bed, bed of powder. So you have I have a grad student working on that project. So the powders, these are all powder. And then you have, laser power source, and then there is one mirror. So this mirror, moves fast. So the mirror, what happens, change the direction of the light. So when it moves, so the laser may shine here. If it moves in this direction, it's gonna shine here. So so the source is stationary, doesn't move. Only the mirror moves, right? Rotate, move, any direction. And when the laser shines to the surface, this powder, it's gonna melt, this powder, right? So it's making one layer of the solid parts. And then you have a recoater system that is gonna bring a new powder on top of the previously solidified material part. So you have fresh powder. And this, mirror is gonna repeat the process. Again, melts, these, powders selectively, not entire section, only in the certain area, depending on what your structure is, what your part is. So this is gonna be repeated all over, until you get, a 3D part. So in this process, what happens, you have a lot of factors that's gonna be involved. Laser power. The laser power should be, sufficient to melt the powder. So the laser, as you see, affects, this is the powder that when they melt, they make, a shape like this. We call it, melt pool. Okay, so this is instantly, less than, point and maybe 100 milliseconds, less than 100 milliseconds. So it's gonna melt this powder and make this, melt pool, right? So that melt pool has a depth, and also once you make one, melt pool, you want to make another, melt pool on next to it. So this melt pool, they have a distance between, the two center. They call it, hatch spacing. So the laser power is going to affect the depth, how much depth you can produce, right? Higher power can produce, the deeper, melt, or thicker material, or the surface layer thickness and surface roughness. The scan, affect the pool size. If you have faster scan speed, the scan speed comes from this, mirror. How fast that mirror can, rotate or move. That is going to affect the scan speed. Then it affects, the melt pool size, solidification rate. How fast your, part is going to solidify. Those, solidification then affects the strength, hardness, surface finish, or scan, pattern. Whether, when you look at that powder from the top, whether the machine can make, island like that, or, and then go to another surface, another part. And this is a strategy, pattern strategy. So you can make your part, the scan is going to, the laser is going to go parallel, right? All of them, they will affect the thermal distribution, the heat distribution on the part. Finally, they will affect the residual stress. Residual stress, residual stress? Residual stress is a stress that is going to be left behind by the process, right? Residual stress normally is not, favorable. It's detrimental to the process. You know why? Because from the strength of material, when you have a metal, right? When you want to pull it, pull the two ends, what happens? You have this stress, strain. It goes up like that, and then something, like this is going to happen. So this is the ultimate strength, right? And this is the yield area. So higher strength is better, right? Is that clear? Higher strength is going to be better. So you want higher strength. But what happens if you have some residual stress? Means your part has some initial stress in there, somewhere here. And then how much stress you can apply before getting to this ultimate point. You're going to be left, by this much. Let's say this is the total is 300 megapascal, right? And then you have some 100 megapascal from the previous process by this, SLM process, and then how much stress you can apply before, failing. You got only 200, right? So that is the residual stress is detrimental. So we want to. That's why we want to optimize the process in a way that we have less residual stress. Okay. So these are the factors. That's why this research about the SLM process is still going on. A lot of when you go to um, sources, open literature like Google Scholar, Science Direct to find research about this process. You see, every day a lot of papers, articles are coming out because it has a lot of factors. It cannot be done in one research. So a lot of factors can be used in design of experiment to optimize the process. Okay. If it was one factor, you can test it one day. That's it. Yeah, this shows some of the pattern I was talking about. Next problem. In car, gearbox, there are a lot of factors that can be changed. For example, the number of teeth, right? How many teeth you can have. That affects the gear ratio. The module define the size and strength of the gear, right? And pressure angle, face width. These are the parameters related to gear design. Okay, only the gear design, those factors. But we also have some parameters related to material, like what material you should use, right? We have steel, even in steel, we have different type of steel. How many steel do you know? We have low carbon steel, right? What else? Cast iron, right? What other steel do you know? Stainless, right? Stainless steel. And even stainless steel, it has a lot of category in there. Whether it is austenitic, when you look at the microstructure, those alloying elements, chromium, nickel, these alloying element changes the property, changes their category. For example, we may have austenitic steel, stainless steel. We can have ferritic stainless steel, right? Then martensitic stainless steel. These are all different category of the stainless steel. And when stainless steel, what does it mean? It means it does not corrode, right? Stainless. You know why? Because it has chromium and nickel. In the low carbon steel, do you know how much iron we have in the low carbon steel? Those steel that we have in construction, bridges. More than 99, maybe 5% is iron. This is low carbon steel. We have only about maybe 2.2% carbon, carbon, very little carbon. But for stainless steel, we have 8%. This is 17%. Then iron is going to be about 55%. We have other alloy elements. That's why when you want to buy stainless steel, the price of this one is going to be double of this one, because this is the only iron. This one has these alloying elements, makes it expensive. Okay, so but do you want to use stainless steel? Has a higher strength, but it's going to cost you, right? You want to decide which material is good. And if you want to use austenitic, then you cannot make it harden. Whatever what strengths it has, it's gonna be that one. But if you have this one with higher carbon, let's say 0.4 carbon, you can make it stronger. Using heat treatment, heat treatment process. With the heat treatment process, you can make this one strong. And then there are operational parameters can be it should be considered input torque, how much torque is going to be applied. So different machine, different car is going to have different torque, right? RPM, lubrication, type and viscosity, they are different for different car. So you see, if for a car gearbox, how many parameters are involved? You want to make it improve. You have to optimize all this process parameters to make it best. So because a lot of factors are involved, then design of experiment come into play. Becomes very handy, helpful to see which process, which factor, which level is going to be best. Okay. So there are some terms. Design of experiment, the term the response. So you have an input. Remember, we have a factor. We change a factor, variable, and then it's going to change the output. Let's say we have a flower or grass. We want to feed. We want to use some fertilizer. We use the low fertilizer, right? One experiment, another experiment, we use high amount of fertilizer. So then the outcome that we are interested is the growth, right? Growth is the response. For that flower, controllable factor is the amount of fertilizer you're using. So as I said, we have some uncontrollable factor that we are not interested. We are not going to look at that one, and it is noise also. It's called noise. Level. So you pick one factor, and then you change it, right? For example, that fertilizer. We have two levels, low amount, we say we're gonna test it, right, today. For this flower, this is the, let's say, 1 pound, it's gonna be considered as a low. And then you use 2 pounds for another experiment that is gonna be high. So this is called level, right? So you pick fertilizer and you use a low amount or high amount. This one is one level. This is another level, right? Level 1, level 2. Then run. After designing, you want to test it, right? You test the experiment, a single combination of all those controllable factor. Replicate. There is a difference between a replicate and a repeat. So sometimes you want to make sure those noise, those uncontrollable factors are going to be removed from the process, and then we use we rerun the test. With one condition, we say, we want to test it with the low amount of fertilizer one day, and then we repeat that process. So if you repeat it another day with the same amount, that is called a replicate. If you do it, if you run it today and tomorrow you run it again, that is going to be a repeating. So it's going to be a sequential. But you run at this one first, and then tomorrow you're going to test this one, and the day after you tested this one again. So this is called replicate. What happens, you bypass, you skip, you did not do sequential. If you don't do sequential, it's called replicate. If you run the experiment sequentially, that is called repeat. We need sometime replicate because we want to remove or reduce the noise or those uncontrollable factors in the process. Okay, repeat and replicate. That's the difference. And then we can use some model to predict the value, which is called fitted value or predicted value. Another way to remove those noises is a randomization, performing the experimental run in a random order. Any question? So, as I said, we have several methods for the design of experiment. One method is trial and error. You just guess. Let's say we have a bakery, and without having enough understanding on how that bakery is going to work, you want to improve the process. You say, okay, I'm going to make a better bread. So I'm guessing if I add this much water, it's going to be better. So this is just guess. You change the amount of water from 1 pound to 2 pounds without doing any study. So this is called guess, right? And then you will see the outcome, whether it was good or bad, right? If you, for the bakery, it might be okay, but you cannot, extend this in trial and error for the large production, for car manufacturing. You don't want to change a lot of parameters and see what's going to be the outcome, right? So that should be systematic approach. So there is no clear or hypothesis in guiding the experiment process. The person said, I'm going to just change, amount of water. There was no clear, hypothesis. If I change the water, probably it's going to make, what is it? The dough better, something like that. Some scientific, hypothesis is not behind this this method. It's just guesswork. Next process, next experiment is called single factor experiment. In the single factor experiment, you pick one factor, and then you realize one factor is going to be very important. So you have some understanding. You see, if I change that fertilizer, it's going to affect the growth. But how much fertilizer I should use? Should I use 1 pound, 2 pound, you use or 3 pounds? So this is going to be one factor, right? You are just changing one factor. You're not changing sunlight. You're not changing the water level. All of them are going to stay the same, right? You're just manipulating one factor. So that is called single factor. So our objective is to see, to isolate the changes in response variable as they relate to the single factor being studied. It's very simple, right? It's simple to analyze. You run the experiment, you measure the growth, and then you plot it and see, for example, you plot the data, right? Something like that. This is the amount of the fertilizer, say F, right? Fertilizer, and this one is going to be growth. And then if you use the too much, probably the growth is going to reduce. Then, so this is optimal place. You find, this is the right amount. This is the best amount of, fertilizer based on growth. We are just looking at the growth, right? So this much is going to be best. So this is, one factor, single factor. But, it's gonna, if you have several, factors that you're not sure about sunlight, right? Or water, amount of water. So you have to repeat the process for every, each one. So this one, it took you, 10 experiments, and then you want to test it, for the water in 10 experiments, and then sunlight, 10. So it's gonna take a lot of time. It's gonna be time consuming. If you wanna, it might be yes. So you find this one, this is gonna be the best for this growth, and this is gonna be best, you run it, and you find, this amount of water is gonna be better. But this is, what happens, sometimes, the factors affect each other. It is not looking at interaction between processes. So when you are doing, single, parameter study, we cannot, find the interaction between, between several factors. Okay. A single, factor study does not give us, interaction information. So we need to do, several factor study to find out, whether we have interaction between those factors. The real world, complexity, changes very rarely occur in isolation. You cannot, isolate, one parameter at a time. So it's going to be, very rare. So it's better to study several factors in the experiment, in the design of experiment. 2 factors, 3 factors, or more factors, 4, 5, because of the cost. Single factor experiment, this shows if we do heat treatment of the metal component, let's say 17.4 is one stainless steel, it's called Maraging steel, and it has, martensitic, microstructure, martensitic. It's not, austenitic, it's a martensitic. And it responds to heat treatment. Some, material, austenitic, as I said, do not respond to heat treatment. So, and then this is the experiment, they wanted to see if they put, the part in the furnace for several, different time, 30 minutes, one group, another group is 60 minutes, and the last group is 19 minutes, right? How does it, it's gonna affect the hardness? And we have the different method for measuring hardness of the material, right? Remember, did you do any hardness testing? So Vickers is one method for measuring hardness, and it looks at micro level. It's not, Brenel or the other method. I forgot the name. Brenel. What was the other name? The other experiment you did for hardness. There was. Okay. Anyway.
Rockwell hardness.
Rockwell, yeah, Rockwell, the macro test. Those, Rockwell and Brenel, they are called, macro. So Vickers is a micro test, micro hardness. Anyway, so they tested, they see, when they put the sample in the furnace for a certain amount of, for a certain temperature, the hardness was 300. And then the 60 minutes, 350, 90. So it is approaching, to a certain value, right? approaching maybe 300, 65, 60, 70 asymptotically to one level. So then they decide whether they want to increase the amount of time or this much, based on the time, right? Based on the cost. So they may say, no, 350 is fine for this 60 because this one is going to cost us money, right? The furnace, you have to burn, gas or electricity. So this is, how many factor is that?
3.
How many factor?
That's a single factor.
This is single factor. And how many level?
3.
3 level, yes. And what is the response? Response in this experiment.
Hardness.
Yeah, the response of this experiment is hardness. This is input, this is output. There are a couple, description example in the baking. Single factor, we want to change the baking time. Constant factors. Oh, when you do, single factor study, all the factors have to stay the same. You should not change it. For example, in that baking, if you are only changing the baking temperature, baking time, and humidity, they will stay the same. And then they pick, 3 temperature, maybe 4, and then they will run the experiment. They will see, how the cake or the bread will taste. They evaluate. Look at this experiment. What are the responses? The responses are written here, right? What is the input and what is the output? Any idea? The input is the baking temperature. This is one level, another level, the last level. So we have 3 levels, right? And what is the response? Taste, texture, and color. So these, may change these output. Sometimes they may not. We want to see. Okay. So how about this one? Chemical reaction rate, concentration on catalyst, right? The constant factor can be concentration, temperature, pressure, and we want to see how the concentration is going to affect the reaction rate, right? So this one, rate, will be our response, right? This is a concentration. These are the factors that we want to change. 1%, 2%, 3%, and then by running the experiment, we will see whether the reaction was slower or faster. Cooling time in injection molding. So the constant, factors are going to be molding pressure. You kept, molding pressure, plastic material. The material did not change, right? Mold temperature stay the same. What is the output? Any idea? What is the output of this experiment? Output is going to be the same as response, right? So that is the term we use in DOE a lot. Response. Review this one and
it's strength and dimensional accuracy.
Mechanical perform. They said mechanical test, right? The mechanical test. What does it give you? The mechanical test. You remember that experiment? The last one. a stress strain curve. That is going to be the tensile strengths or Young modulus. Those are the factors, those are the information that you get from mechanical test. So the output here can be anything from this experiment. The strength, modulus, yielding strength, also ductility, right? Elongation. Another thing that we can get from here is called toughness, measuring this one, the area under the curve is called toughness. So these are all the information that we can get from simple tensile testing. We may have other mechanical tests, but this one is a very general. Okay, so these are the this is the factor, input factor, and this one is the level, first level, second level, and third level. So we have this experiment, let's say we have a machining process. So we are looking at the machining speed and surface roughness, okay? If we change, the factor is gonna be cutting speed, SFM. We wanna see the optimal cutting speed for minimizing surface roughness, right? What is the input and what is the output? Input is cutting speed, right? We use different, cutting speed, and then we are looking at surface roughness. So these are parameters that they will stay the same. We don't change them. So the procedure, we set up the machine, and then run the experiment with this, three level, 100 SFM, 150, and 200. So once the experiment is over, you measure the surface roughness. The first machine, you see, you got 1.2 micrometer. So that is roughness for the first one. Second one is this. Last one. So as you see, the lowest one gave you a large amount of roughness, as well as the highest SFM gave you very large surface roughness. So if you want to measure the average, you can simply take average of all these three, and then that's going to be the average. But by plotting the data, you can find this one as the minimal surface roughness, single factor study. We have full factorial. I think that is gonna be too much. We can cover the full factorial experiment on Wednesday. Okay. Any question? Do you have anything to share? No. Okay. We have no class activity today. I'll see you on Wednesday.